Hello and welcome. I'm Stephanie Hendrickson, Executive Editor for Additive Manufacturing Media. I'm pleased to be moderating today's webinar brought to you by Endeavor 3D. Today's presentation is all about optimizing the product lifecycle with 3D printing. So this webinar will dive into different ways of leveraging additive manufacturing at the different stages of that lifecycle, including product development, tooling, spares and repairs, and full-scale production. Our speaker today is Daniel Baker, the Program Manager for Plastics at Endeavor 3D. Thank you for joining us, Daniel. He has spent his career in additive manufacturing with experience in contract manufacturing, part identification, and process optimization. At Endeavor 3D, Daniel is responsible for managing strategy, planning, and execution for the plastics program. So I'm going to turn things over to Daniel in just a minute here, but first, a couple of quick housekeeping notes. First, if you look to the panel on the right side of your screen, you should see up there a Q&A tab. If you have questions for Daniel at any point during the presentation, please submit them through that tab. We'll save time trying to answer as many of those as we can at the end. Second, do want to let you know that this webinar is being recorded. You should get a link to the recording in your email, usually within a couple of hours. So if you're not able to stay with us for the whole session today, or you want to reference it or refer a coworker or a colleague to it later, that recording will be available. So all that being said, I am going to head backstage until we get to the Q&A and turn the floor over to Daniel.
Thank you. Hello, everyone. Thanks for joining this afternoon. What a great intro. So I will just go ahead and kick us off. Today, I'm going to talk about optimizing the product lifecycle using 3D printing. Quick intro, Daniel Baker, Program Manager of Plastics at Endeavor 3D. I've been in the additive industry about 10 years. Most of that time on the operations side, heavily focused in polymers. So all things, plastic nesting builds, sending builds, redesigning parts, kind of cover the full cycle. And then a little bit of background on Endeavor 3D. We are a contract manufacturer just outside of Atlanta, Georgia, out in Douglasville. We have a very large 65,000 square foot facility dedicated to additive manufacturing of polymers and metals. 9001 certified, and we are part of HP's digital manufacturing network. Industries we serve are pretty broad, but I would say the highlights are really automotive, healthcare, consumer goods, and then a few defense and military applications. Services we provide, full sweep of all things 3D printing. We'll start with design and engineering services. So if you have a part that you need designed, we do reverse engineering with 3D scanning. Anything on that front we can cover, or we can support you in that effort. Obviously, the printing, the post-processing, and the sintering of all of our parts. We have a state-of-the-art QA lab outfitted with quite a range of equipment. So if you have a need there, whether it's scanning, getting data on your parts, testing the powder or the raw material inputting into the system, we can cover that, and then fulfillment and packaging on the back end. Quick agenda for the day. We'll cover three main topics. First, I'll give a brief overview of HP's multi-jet fusion technology, which is what we will focus on today. Then I'm going to go into a deeper dive into some applications and design guidelines for the HP multi-jet fusion process. And we'll close the presentation today with a review of the additive lifecycle and where parts fit into each of the kind of defined segments that we have broken them out into. Really quickly, a poll is going to pop up in the chat in just a few seconds, asking you what your level of 3D printing experience is. Feel free to kind of answer that at your leisure as we continue the discussion today. So, technology overview. We'll jump right into HP's multi-jet fusion process. HP has developed an end-to-end solution for our additive manufacturing needs. It's really a fully integrated platform controlling your print data, your material management, and your production all in one simple kind of combined ecosystem. HP also really leads the industry, in my opinion, in software development, whether that's partnering with third parties, such as, Autodesk NetFab or Materialize Magics, or with their own kind of proprietary software in the command center. They really help you track the full sweep of production from, part being input into the system, so that digital CAD file going to your printer, tracking your material and agent consumption, your print yields through their proprietary software, as well as kind of the back end production workflow as I mentioned, partnering with third parties and MES systems that really integrate all of that into their platform. So how does the process work? I'm going to kind of break it down into 4 pretty simple steps. The first, the inkjet print heads apply the 2 different liquid agents across the print bed. So that's what you're seeing in bucket 1 there. You've got 2 different agents, a fusing and a detailing agent, being dropped onto a bed of powdered plastic. The 2 agents here, the fusing agent really defines the powder that's being fused, and the detailing agent is provided at the cross section, the boundaries of every part, to really suppress the thermal conduction, and that's how HP gets the really high print accuracy that we see throughout their process. And then when you look at number 2, energy delivery, the powder bed is heated by radiant energy. All of the water and other like volatile compounds in those liquid agents are evaporated, and what's left behind is melted and fused into your final part. From there, you have a Z-stage retraction. So your part actually goes down into the print bed. So you're not building up, you're kind of building in reverse downward. The printed part also moves down with that bed of powder. And then finally, if you look at number 4, a new fresh layer of powder is deposited on top of that, and the process is then repeated. Here at Endeavor 3D, these are the materials that we offer today. There are a few other materials on the platform, but we offer both their original nylon PA12 and their newer nylon PA12 white. The main difference between the 12 and the 12 white is simply the color that it comes out as fused. So if you've seen a multi-jet fusion part, historically they're this kind of natural off gray color, and that's due to the agents that are being used to bind that part together. They've recently come out with the white, which gives you a clean white finish, which we'll go into in a little more detail in the next slide. We have their nylon 11 as well. This is a great alternative to the PA12 if you need, a little more impact resistance, or you need a more sustainable material, as the nylon 11 is a natural material. And then finally, we have their TPU, which is good for any kind of rubber-like application. You need something with flex. It's about an 88 Shore A, and that provides, a great alternative to, the typical nylons that we offer. Looking here at the color solutions, I kind of teased it on the last slide, but with the addition of HP's 5420 series printer, we can add bright, vibrant colors in our post-production capabilities. So using this material, we center a pure white part, and that opens up the ability to dye or any other post-processing that was limited by the darker gray color of their previous part. We at Endeavor are partnered with Dimension, so we use their full suite for our coloring capabilities, and you can start to get neon pinks and neon blues, which you previously weren't able to achieve on the platform. All right, with the housekeeping out of the way and what we do at Endeavor 3D, let's jump right into some application and design guidelines. So I'll start with what I think is the most critical, depowdering. It has to happen on every part. It's an essential step in the multi-jet fusion process as we're working out of a powder bed. Since the parts are suspended in that powder bed, we have to successfully remove all of the powder from the parts during the process. Historically, this is a pretty labor-intensive process, and it's prohibitive for larger volume run productions because each part has to be handled manually. There are a few options that we have here. The first is automating the depowdering process. HP has developed a system that will kind of remove this first step that you see on the screen, where an operator has to vacuum that powder off of the part, which enables larger batch, higher volume runs with a little more efficiency. But we can also think on the design side, how can we depowder our parts more efficiently? So when we think about that, the first step is really, are there any blind holes? Adding relief to those features will allow the media we use to remove that powder a little more efficiently. If there's an exit hole, you have somewhere for that powder to go or to quickly be removed. Another option is something like a sacrificial feature, which I'll go into more detail on the next slide, but something like an auger that can be removed in post-processing, taking the powder with it, which, kind of shortens down that labor step, and everything, is ultimately going to lead to cost. How do we drive cost out of the part through design while adding, a functional feature in the part? So if we look at this depowdering step, the auger, long thin channels are notoriously difficult with any kind of powder bed process. Think multi-jet fusion or SLS. So how can we get the powder out of that interior cavity or channel? Something like this auger has been very successful at high volume for us. So through CAD, you design a simple structure. It's going to look different part to part. It's really kind of tailored to the specific channel that you're focused or feature, or the feature that you're focused on. But once you have that, you will pull it out almost like a plunger. That auger is then, fully sacrificial, so it is kind of a waste in the process. One thing to think through is a lot of our customers or end use parts that they want to remove as much material as possible, because traditionally in injection molding, the lower the material, the lower your cost. However, since there is a significant labor step in the depowdering of these parts, a lot of the time it is actually more beneficial to add just a small amount of material that may be sacrificial to reduce that kind of waste of time during the post-processing step, or to increase your yield with, if you have clogged channels or somewhere where you can't get that powder out, you're going to have a less effective or a less efficient part. Now we'll go into some other, design guidelines. Let's look at assembly features. So a great aspect of HP's printing process is that you are suspended in a bed of powder, so you don't need supports like many other additive manufacturing methods. So complex structures, living hinges, snaps, set screws, all of those can be designed into your part without having to do an assembly after the fact. So if we look at the picture on the bottom right, that snap there with HP, those are actually printed in place. So with enough clearance, you can actually leave them together, printed in place, and it's a functional a clip. So a better real use case example for that is this hinge. So it was modified specifically for this printing process through HP. So while the assembled ring itself has a relatively large footprint and what I'll call dead space in the center of it, again, you imagine this is in a 3D box. You have a lot of space in the center of that assembled hinge where you're not actually printing parts. So by opening up that hinge and on the as printed side, printing it in a flat, straighter line, you maximize the throughput and the efficiency of the part in the process. What this does is it drives down the economics. It also drives up your throughput, which allows you to kind of bridge from, that bridge production to full-scale volume production. Simple change like this, which I'll dive into in a few slides, drastically affects the overall outcome of the part. Some more assemblies, just kind of showcasing ways to think about your part. Historically, if you have these two parts shown on the left, you're going to print them as two separate pieces and then assemble them after the fact. As I mentioned with that clip, a benefit of the powder bed process and multi-jet fusion is you can actually print them in assembled form. One, it saves space in your build. Two, it reduces your cost in assembly. And again, it's all about leaving clearance as you're printing. You don't want the parts to fuse together. If they're touching or they're too close in the build, they will start to fuse together. But as long as you leave a minimum clearance, you can start to print parts in assembled form as long as that powder is able to be removed. Another good design guideline or example for HP is part consolidation. We hear it a lot in the additive industry. Is additive enables part consolidation. You can redesign all of your parts, but a real life example of this shown on the screen is this duct here from HP. So at the top you see the injection molded version. It had 14 components, I think 7 unique components, and all of that was redesigned down into one printed component. What that does is, and what you'll see on the next slide, it reduced the cost significantly. There's no capital expense for the tooling. and we're also able to modify for performance. So looking here, there are no seams, so the airflow is actually improved through this duct. And as I mentioned, it has 7 unique components redesigned down into one, and it fits perfect on the platform. The next major topic that we'll cover is build packing. As I mentioned, almost everything leads back to cost and efficiency as we're looking to do production scale. So focusing on build packing or nesting isn't something many designers think about today, but on the contract manufacturing side and in manufacturing in general, that's what's going to kind of drive our throughput and our efficiency on the process. So there are a few options to consider when you're nesting parts. From a design standpoint, the first point of consideration, is this an assembly design where multiple parts are being printed together, like what you see on the screen? Or are you only printing one single component, as that will look different? And it's critical to think through this at the beginning of the design phase, because multiple geometries, like shown on the screen, tend to nest together more efficiently, right? If you have multiple types of designs and types of parts, they're going to slot together a little easier. And say, if you have one housing, you're always going to have a dead space, or that hinge from the previous example, you're always going to have that open space in the middle. And so it gets, significantly harder to nest those. So you have to think before you design, how are these going to fit within the constraints of my manufacturing process? So simple way to think through this, there are 2 ways that we nest. There's the XY nesting, which is a simple 2D. You've got a 2D plane, you put 2 parts like a puzzle piece together. How do they fit? Keep in mind, you have to keep a few millimeters of separation from your parts so they don't fuse together, and you can manage the heat within your build. And then we also have the ability to nest in the Z. As I mentioned, you're suspended in a bed of powder without the need of supports, so you can stack parts on top or inside of each other, like you see in the Z nesting example. Bringing back this clip design, you can see on the left, as it was designed. So if we did not modify the design at all, you would have 108 total parts. It takes about 11 and a half hours to print at a 5.8% density. But by unfolding that part, printing it flat, you nearly double the density of the build, which effectively halves your manufacturing cost, because you're printing twice as many parts in the same amount of time. And you're at about double the density, which then drives down your per part cost, because you're amortizing that powder that's being used in the build over a much larger number of parts at a higher density. So then when we're recycling at the end, you save that powder cost. And as I mentioned, the 2 ways to think about it are the assembly or an individual part, how you nest. So if we look at the left, that is showcasing, one part repeated, nested in the build, and nothing else is within that. So that part is a great example because it's kind of a boxy design. It fits well in the build box, and you don't have the dead space like we had in that hinge design. However, it's not always the case. And where we typically live is in this anchor or Kanban design. So anchor is really, you got one large part, which would be prohibitive. A lot of the times people don't want to come to additive with larger parts because the cost is prohibitive to print one or many of those. However, if you have the rest of an assembly or other parts in that design that you can nest around that part, you start to lower the cost of those larger parts. And then Kanban is another great example for specific assembly designs, where if you are running one program, say with 10 additively manufactured parts, you would want to print all of those in quantity 10 each time. So we will try to nest the production builds in such a way that they are full assemblies nested together in even quantities. That way I'm not printing, a build with 5 of these one part and 500 of these other, and I have to have 100 builds of build A to match my delivery for one build of build B. The last topics we'll cover here are cosmetics. So on the printing process itself, there are some considerations on where your part is located within a build. And that correlates to how the surface finish or the A or B surface will look. You also need to consider warpage and your mechanical properties of your part as well. So first, we'll look at cosmetics. The cone on the top here is showcasing how build orientation will ultimately affect your part. So rounded surfaces, it is a layer by layer process, but you're not going to see layer lines like you would, say, on an FDM or an FFF part, where you're building them single layer at a time. You will see, slight, like a disco effect is what I will call it, but like ringing on your part, where that powder is being stacked on top of each other and the parts are being fused. And so complex surfaces, you want to orient in such a way that you're limiting the cross section of that part being printed. And then same on the bottom, looking at text, there are just some small considerations where embossed text is face down in our build box, and debossed text is faced upwards. Now looking at mechanical properties, I mentioned you want to optimize nesting for the efficiency of your part. However, there are limitations. You typically want to run anywhere from 8 to 12, 14, 15% density within our build box. So the example with the X there is just a large, dense cube. If you have too much material being cured in any given cross section, you run the risk of essentially damaging your powder. You're providing too much energy into too localized of an area, and you start to degrade that nylon powder in the printing process. So how do we limit that in our design? It's either lightweighting, so utilizing a lattice design to kind of limit the cured material in your part while maintaining that same strength that you're looking for, or you spread those parts out throughout the build, as you see on the right, and you limit the individual cross sections on every layer of that build. So key takeaways on the design side: there are limitations within the multi-jet fusion process, and it's important to know those if you want repeatable parts, but it's also important as you look at the life cycles coming up, it's important to incorporate those in the beginning of your product design. So as you're starting to think through product design, you want to start incorporating these design rules right away. So you're not, facing a redesign midway through a project or down the line once you ultimately decide, to do bridge production with additive, for example. Features like hinges, buckles, and snaps can be beneficial for not only assembly, but also can improve your part economics. As I mentioned, printing in place is a great way to do that because you limit the footprint within your build. And then orientation and spacing of your parts are critical, not only for the surface finish and the warpage, but mechanical properties as well. And now that we're through those design guidelines, let's take a look at the additive life cycle, and we will look at a few examples from our partners at HP on how they have incorporated additive into each phase, each of these phases. So first, I'll define the 4 key archetypes for the additive life cycle and where additive adds value in each of those. So first, prototyping. This one's really should be no surprise to anyone. AM has traditionally lived in this space since its development. Quick turn parts at a relatively low cost. Prototyping will always be supported by additive. Bridge production is number 2. So as you ramp production, utilizing additive for development or pilot runs is a great low-cost alternative. It provides the engineers with the flexibility on their design. You get quick feedback and can kind of do those design loops at a much more rapid pace. And you're not wasting time waiting 6 weeks for a change in your mold or to get your parts. You're also kind of limiting the capital expense. While your piece part price is typically higher than injection molding, you don't have all of those capital expenses tied into a tool. So you can start to modify and refine your design before going into high volume production. Full production. This is relatively new for AM. There have been a couple use cases, that were historically where additive was used at, relatively high volumes, but over the past 5 to 10 years, we've seen increasing adoption at very high volumes for a number of industries. As the processes, not only multi-jet fusion, but the industry in general, get more repeatable and reliable, additive opens up those design, guidelines and opportunities where we can start to add function or add performance benefits through our design while holding a competitive cost. And I would say key industries that we see here are aerospace, automotive, and consumer goods, where they've adapted additive at full-scale production on quite a number of components. And then lastly, we'll cover end of life or spare parts. At the end of the life cycle, a production part, typically you struggle on how do I get those spares or key replacements. Are they locked on a shelf in a warehouse somewhere? Do you have to order a large quantity once you're kind of retiring or sunsetting a design and application? This is where additive can be used to qualify that part earlier in the life cycle. And then you can have key on-demand spares without, having to order massive quantities or kind of guess how many, spares or replacements that you're going to need. So to frame, the end of this presentation, we will use a simple product lifecycle approach. In this graph, you're going to see low volumes during development, ramping up as you hit production and high-scale manufacturing, and then winding down for the kind of spare parts or end-of-life part production. So depending on the business and the specific part, additive can really play a role in all of these ranges. And today we're going to look at those examples from HP, how they identified internal products within their brands at each of these phases, and then ultimately how they made the decision on when, where, and how to utilize AM across those business models. So the first is prototyping. Like I said earlier, it's pretty obvious that 3D printing is a tool for rapid prototyping and product development. There are hundreds of thousands of parts that have been prototyped utilizing additive, and many things can fit into this bucket. Basically, any new design or test market can utilize prototyping with AM. You're not waiting on a tool. You're not waiting on parts. You can get parts as quick as 1 to 2 days, throw them on a printer, get the part, rapidly iterate the design, and then continue moving on through the cycle. The next example, we'll look at the end of the life. So this is the spare parts or any kind of replacements. Where does 3D printing fit into that? And how does it fit into the procurement process? We find that, most industries see this as a really big pain point. A lot of capital is tied up on a shelf or a warehouse. Engineers don't know how or where to order parts from. They may not have the CAD. They might just have physical parts at this point. So how are you, getting those parts converted to digital CAD and then replaced? That's where additive can really help fulfill all of these aftermarket service requests. So in this example, HP has a great case study on spare parts using their own manufacturing process. If we look at their large format printing, these things often have a lifespan of 10 to 20 years, which exceeds the typical production for each of the models. However, there's still a need to service those machines, keep them running, and at a certain point, HP has the decision to make what they call a final buy, where parts are ordered for the last time, and that quantity is supposed to fulfill the rest of the life of that install base. Typically, they warehouse these parts, and they're used only when they're needed. So they identified clearly there's a use case for their own manufacturing method here. And maintaining and creating that digital inventory was critical for a number of these components. So looking at qualifying those parts, as I mentioned earlier, it's important that you qualify them earlier on in the process, so you're not doing that kind of end of life. So as they're developing new large format printers, the process that HP is going through is they're qualifying it for molding, but simultaneously qualifying those parts on additive. And what that does is once it hits the end of life or the kind of end of life of that specific model, they already have parts qualified on their HP Multijet Fusion process. So we're able to just pull the digital file, pull that locked build that they were running, and produce those spare parts on demand for their end use customers. Before we jump into bridge production, which is the next major step we'll cover, just thought it was important to talk through another pretty prominent use for additive historically, which is jigs, fixtures, tooling. These really encompass the full life cycle. So it's not specifically in development or in volume manufacturing or spare parts, but it lives kind of along the life of the chain. And a great example where additive fits into that is another HP example for their print head manufacturing line. These print head nozzle, this drill extraction shoe is used during the manufacturing of the print head nozzles to remove silicon sludge and water from the machining process. It's essentially an efficient way to make the process easier, faster, cleaner. What they looked at was they have this highly complex, over-engineered aluminum tool on the left. It was a rough cost of about $450 per unit. The 7 parts had to be assembled, and it typically, they had a minimum order quantity, and it took multiple days to get one machined and then assembled. Looking at that same part on the right, they were able to reduce the cost about 95%, going from a machined aluminum to a printed plastic, while achieving the same function. And this is a low volume, low impact part, but a drastic savings just by kind of changing your mentality of the part has always been CNC'd. Why not 3D print it? It doesn't need to be aluminum. Nylon 12 is a suitable material. And then you ultimately end up with a better, more efficient part. Now we'll continue on the curve and we'll look at bridge production. Bridge production is been more common in the additive industry over the past few years, especially as you want rapid product development cycles, you want design iterations, and you want that feedback as you're going to market. What's nice about our multi-jet fusion platform is the printing time is relatively quick. It's about 11 hours for a full build. You do have to let those parts cool, but you can start to service customers in 2 to 3 days with end-use production parts. So another example from HP's business model is this HP 3D camera. This was a brand new development project for them. There was no history of this. There was no market for this. So since that was the case, speed and learning were their 2 priorities on this project. They wanted to get the product out to market quickly. They wanted something developed, and they wanted to iterate within days rather than waiting, weeks for a tool or a design cycle change. So all plastic parts within this entire assembly were printed on our MJF platform. Something that to note is from a cost perspective, that drove out about $50,000 of capital expense. There were no tools that needed to be made. So all of that savings, while the piece part price is higher, went directly in to the production of this part. You reduced, as I mentioned, multiple weeks for every design cycle and iteration, which let them get to market first and beat the competition on speed. And then they were ultimately able to keep one of the parts multi-jet fusion for full-scale production just because it made economic sense. So since you're not injection molding all of these parts, you're able to change the design while still qualifying it for injection molding. So that was the intent was never to keep these parts at full-scale production on additive. The intent here is to move the parts through additive in the early life cycle, do low volume runs as you're kind of ramping up to those higher volumes. And then once you hit that break point, there's always a break even, whether it's 100 units, whether it's 1,000 units, on when it makes sense to cut a tool. And that's what HP did here. They started to run it, they iterated, and they ran the first kind of Gen 1 version of this part using additive. And then once they hit the volumes and they knew the market was there, they decided to cut a tool, move to injection molding. And then similarly, if we kind of follow our curve, once it hits aftermarket or end of life, or say the tool hits its life, we can then move the part back into production just for service or smaller quantities. But to truly unlock the full potential of additive, we have to break that mentality of just prototyping or small volume runs and really identify applications at scale for production. That's been a turning point for many companies over the last decade. And we're going to look at a couple more examples internally from HP on how they identified products early in the life cycle and moved them to true volume production. So for full-scale production, it's a pretty easy task to identify where AM can fit and like what parts can be AM. But the goal is really to think through highly over-engineered components and to see if with redesign and modification, can we keep the same function while costing out and then removing that initial capital expense from our business. And while they're not the flashiest components, something as simple as a small, simple bracket or a housing are great places to start when you're looking to identify parts for volume production. So an example here, what you see is the design progression for one of these components. It is a very simple plastic part. It was typically machined aluminum. However, it started as a machined block and ended as this topology optimized, weird looking structure. What that shows is, you don't have to jump to the final version at the beginning. It's a progression. So through this progression, we start with traditional machined aluminum. We then print that exact or very similar part as a plastic 3D printed part. Then we want to start to cut weight and start cut cost out of it. So we lightweight it either through latticing or just simply removing volume from the inside of the body. And then lastly, you run through, software simulations and you optimize that design for the same function and same strength, but the lowest footprint and the lowest weight possible. In this specific part, HP was able to cut 50% of the total cost to manufacture the part out, 93% weight, and then a 95 times carbon footprint reduction. So how do we get to that, bracket? How do we think through that? As you identify production parts, most people go through this kind of down selection model. So first, you're going to look at, where are the opportunities within, my specific part or my specific assembly where I can utilize additive. In our case, we're talking only polymers, so we'll look at our plastic or our low tech parts. And then we look at how can we make it work? Does the material work? Does it fit within the build volume of the manufacturing method I'm looking at? Can that method hold the tolerances? And then most importantly, and typically, what comes at the bottom of the funnel is it cost effective? Using this approach, when HP went through this process that we looked at on all of those different models, all of those printers for full scale production, they landed on only 25 parts, fit that initial kind of review of does it work for additive? And so the question is, as we look at, changing our mindsets, as you engage in this process, how can you widen that down select criteria, incorporating not only the benefits of AM on design, assembly features, assembly reduction, but also can you get more function out of your end use part? So starting to widen that funnel allows you to, think earlier in the process, can I design this in a different way where I'm not competing with that machined aluminum or that injection molded part, but I'm designing an end use part for additive manufacturing, or I'm consolidating 8 of those components into one. So while a piece part price is higher, I'm reducing 8 pieces out of the BOM. I'm reducing that assembly so that my cost starts to make more sense. And then lastly, we touched on in the beginning in the design guidelines, and I noted it was one of the most important, but can you design for packing and the density for manufacturing in your initial design so that they nest well together? You're going to get the most efficient, most useful build possible, thus further reducing your overall cost. In doing that and kind of consolidating all those parts and going back to their engineers and rethinking what they were able to do, HP moved from 25 parts identified that made fiscal sense for additive to over 140 components on their printing line. And as engineers, many of us know and you understand how much time is spent waiting during the product development cycle, especially waiting for tools to be built and receiving your parts. This cycle is only kind of exasperated by the redesign loop, which integrates your product improvements and learning and all of the feedback that you're putting into your product. We're no longer kind of waiting on this redesign loop with additive because it's a much shortened, much simpler process. You go from part design to design for additive manufacturing, you build it, you test it. You're not waiting on the back end of the process. So you can loop in days rather than weeks. And that's it. Any questions in the chat?
All right, thank you, Daniel. So yeah, as a reminder, if you have questions, please put them into that Q&A tab, and we'll go through as many as we can here before the end of the hour. Just to kick things off, are there particular design tricks or textures that you find are useful for specific applications that you're dealing with?
Yeah, I mean, it's going to be application dependent. But I think the biggest kind of design trick I would say for manufacturing is I'll just kind of back through. It really starts with the depowdering process. So if you're looking at any specific additive part and you're considering a powder bed method, whether it's HP's multi-jet fusion, SLS, anything with powder involved, you're going to really want to control your blind holes or any kind of cavity within your part. It even goes, into, take a generic housing, something like your phone case. You're not going to want any sharp corners. You're not going to want anywhere for that powder to be kind of trapped or stuck into your part. So adding a fillet on those internal edges, opening up holes like you would see on the screen here, would allow for the powder to be removed and your end part to be more functional.
All right. Question in the chat here specifically about medical applications. With PA12, is there any specified time limit for skin contact? And are all of the available colors allowed for use in skin contact prints?
Yes. So there are. We can. I'm happy to share that they are all biocompatible for touch, and then all of our colors as well. So if you have more questions on that, feel free. I've got my information here on the last slide. If you want to just shoot me a note, I can send you all of the specifications for biocompatibility for not only the materials, but the colors and post processes as well.
Awesome. All right. I guess maybe just take a moment. Can you talk a little bit about the reasons to choose multi-jet fusion versus some of the other processes that you've alluded to? So we talked briefly about FDM. Selective laser sintering would be another powder bed plastic process.
Yeah, I think there are a number of benefits. So each process is really going to have its own niche or kind of area where it lives. I don't want to say one is better than the other kind of explicitly. It's going to be application and kind of user dependent. But for your generic part, HP is significantly lower cost. It's a little faster. It's very reliable, and it has extremely high accuracy. So for us, your first print yield off of an HP printer, is going to be something significantly higher than say you would see on FDM, where you're going to have a little more variance. You're also getting relatively isotropic parts because we're fusing and not using the layer by layer process. Our parts are strong in the XY, but also the Z. The limitations, I would say, are the material offerings. I mentioned that we've got a thermoplastic polyurethane, so a rubber-like material, and then we have nylons. And so not every application is going to fit within those specific material constraints. But if you have those materials or something that is suitable, if those materials are suitable for the application, I think HP is kind of world-class or leads the industry for those.
So I want to follow up on, you showed us some really complicated and interesting looking build strategies, just how you nest all the parts into the printer. Are there software tools for that, or how do you learn how to the best practice for how to do that?
Yeah, there are a number of tools out there. HP provides one off the shelf. Autodesk NetFab has a center module. So they have different kind of algorithms that will move your parts where you can constrain the XY or the Z or the part rotation, how it moves. We actually use Materialized Magics, which is pictured on the slides. Let me grab that. So these slides here, these are just actually like screenshots from Materialized Magics. But what it does is you actually, on a part level, you dictate the orientation or its freedom. And then the software will actually take those constraints, how far apart the parts need to be, how much spacing, if they can interlock or they can't. It's a little hard to see, but like a great example is on the anchor slide in the middle there. There's a small part inside the open mouth of that duct because there was enough space to kind of use that free volume to pack a few extra parts. But it will run through its simulation and then kind of spit out the final result. Otherwise, you can manually nest them. It's just a little harder to move them efficiently and separate them in a build.
Very cool. So I want to ask a little bit about kind of like using additive as a bridge production method before you get to the point of injection molding, and like how do you think about transitioning a part if you've done all of this development to make it work for 3D printing? Like how well do the requirements sort of mesh there, or is it the case that you might have to be doing some more redesign to get it to an injection molding point?
So for us, it's a little easier. I mean, that's maybe another benefit to sell for HP in the multi-jet fusion process is you're not limited as much on the design constraints as say other technologies like FDM, where you would have to have a ton of support material, or SLA where you're adding that support material. We can typically print parts designed for injection molding, so you can have your draft angle, you can have all of that pre-designed into the part, and you're not having to modify that post bridge production. I would say that's the most common that we see is, a customer knows that this is eventually going to be outside the scale of our production process, and they're going to want to make hundreds of thousands of these at a relatively low cost. So what we'll try to do is, look at the total value of that additive life cycle for our customer, and we'll look at it and say, this makes sense to run up to about 1,000 units, and then you should probably cut a tool and go to injection molding because that's where your piece part price, the two cost curves intersect, and it's going to be cheaper for you in the long run. But on the design side, with HP, since it's a powder bed process, no supports, you can typically just live with the injection molded design and print it as is, so they're not having to modify, and you can qualify both together.
All right. So in your experience, do you see a lot of companies that are getting spare parts produced? Do you see them substituting polymer for metal frequently?
It's very common for us. I mentioned it at the beginning, but one of our services is 3D scanning and reverse engineering. We're just outside of Atlanta. It's pretty heavily manufacturing focused out here. And so we actually have a lot of legacy shops that don't have digital versions of their parts anymore. They just have old legacy parts that have been kind of phased out of production. And then they need a few spares here or there that are kind of critical for service or warranty for their end use customers. And they will typically bring over either a machined part or just a legacy part that they had from molding, have us scan it, turn it into digital CAD. And then what we do is we create a library of spare parts where those parts have been qualified, the customer's happy, they kind of meet all the criteria. And then similar to like kind of what you see on the screen here, these builds, we actually lock that build, lock that orientation of the part that we know that works, lock the software that was tied to it on the printer, and then we can repeat that process, whether they need one, whether they need 100. It's just a simple process of adding those back into a build box, setting them to a printer and running those. And then converting metal, it depends. There are a number of applications where, I think I showed a few aluminum in the presentation, but they're either aluminum or steel machined, and they don't need to be. So we can move that to nylon.
All right. So we talked a little bit about getting, you showed like the auger technique, how to get powder out of difficult places. There's a question in the chat about enclosed hollow parts. Like, is there any way to print an enclosed hollow area through MJF?
Yeah, you have two options. You can print them enclosed or hollow, or you can add like a relief. So what I've seen is say you're fine with you've got a hollow sphere. There's no way to get the powder out. You can leave the powder on the inside if that's okay. If the part is fine to be dense, it will just be uncured nylon powder. So say you've got a couple millimeter thick wall, then you'll have powder trapped on the inside of that. It's packed dense because it's being packed as it's being built in the process. And so you can have it live that way where it's going to reduce the weight. You're not adding that binder, so you're not actually curing or melting any plastic. It's just going to be powdered nylon on the inside. Or in CAD, you can add a keyhole or some type of feature that is removable. And so on that same sphere example, I've seen them where I'll print those as separate pieces. I'll remove the powder from that hole or that open area, and then we'll reapply in like a post process that keyhole back to the part, either glue it in or have a snap feature where it locks in, and then it seals back up the inside of the part.
All right, I think we maybe do just one more question here. So how often are you presented with a brand new part versus trying to recreate something that already exists? And in those cases where it is a brand new design, what indicates to you that this is a good design for 3D printing, or this isn't a part that's an opportunity for 3D printing, or maybe this should be injection molded instead?
Yeah, I think we're in the contract manufacturing business, so most of the parts I see are new parts, at least to me. So typically, our customer base comes from some level of kind of engineered knowledge with 3D printing. It's become a lot more accepted and kind of more broad, I would say, across a number of industries. So when we're working with design engineers, they typically know about 3D printing. They just don't know the nuance of design for specific processes. And that's what they're looking for, is kind of engagement on what additive technique or process should I be using. And they might not know MJF exists, and like we'll have to explain all of that to them. But the DFAM process is pretty simple because most designers are designing for molding because that's how they know. And it's just a few small tweaks or changes to optimize. And then once you kind of get into what I talked about today, like nesting, for example, it's a pretty easy visual to show you. Like you've got a 15-inch by 12-inch by 15-inch box. The more you fit into that box, the cheaper your part is going to be. And then they start to see that, and they'll either work on assemblies or splitting their part into multiple pieces, or consolidating assemblies to fit in that box to really drive that cost out. And then we are, as a business, very transparent on injection molding. So I will always kind of tell you, here's your cost curve, and then a rough cost of a tool. We know what that is. Like, here's your piece part price. Again, your break even, whether it's 20 parts, say it's a large housing, or whether it's 2,000 parts, we'll kind of share that with them so they know kind of what minimum order quantities or what volumes they need to be competitive with other technology methods.
All right, I think we'll leave it there for today. Daniel, thank you so much for this presentation.
Yeah, before we drop, I've got one plug. I missed our marketing slide at the end, so let me grab it. Just a couple quick shout outs from Endeavor 3D. Next week, we will be at MPE, so stop by and see us at our booth. I will also be giving a workshop on Part ID to quality mass production, where we will be covering some of our automotive components, how we kind of went through the early PPAP phases, qualified them for production, and then ultimately are running those at full build production now. And then we have a white paper launching in early May, all about bridge production and really how to kind of go from prototyping to bridge production with additive. So if you're interested, please reach out to me via email, and we will send you a copy.
Awesome. And one last reminder, if we didn't say it in the presentation, there is a handout in the handouts tab with some more information about Endeavor 3D. So thank you everyone for attending. Thank you Endeavor 3D for making this possible. Again, the recording will be available in your email, usually within a couple of hours. And if you're heading to Orlando next week, we hope to see you at NPE. Thank you.
Thank you, guys.